Good morning, everyone. So as already was said, this is a joint talk. So halfway, my colleague Meissa will take over and he will talk then about the rotational part. So my name is Frank. I will first describe of this topic. So the rotational level intervals in HD from sub-Doppler Rovibrational spectroscopy. I will first cover the Rovibrational section. Okay, so Rovibrational spectroscopy in hydrogen. I think we all agree it's also an excellent testbed for fundamental physics. So it's the best calculated neutral molecule, as it is a simple four-body system. That makes it an excellent test for molecular QED theory. We can potentially extract fundamental constants if the theory and experiment are in agreement and equally accurate. Or we can even go into physics beyond the standard model. And I always like the analogy or the comparison with the Kelvin distortion balance, where you extract a big G, and you could picture the hydrogen molecule kind of similar, where you have two test nuclides with a certain distance, and depending on the vibrational mode you're in, you can increase the mean nuclear distance. And as you see, even V14, my colleague Kenneth will talk later this afternoon about high vibrational states actually. So, but in order to compete with modern atomic systems or ionic systems, we need to extract kilohertz level of accuracies in order to contribute to several of these problems, or a relative uncertainty of below 10⁻11. We do spectroscopy in HD, as earlier explained. We want to exploit the smaller permanent dipole moment such that we can do dipole transitions. And here depicted what we do. So we measure from V equals 0 to V equals 2, and we can then access the R branch or the P branch. So the most naive way of doing absorption spectroscopy is what we do is just having a laser, and you have a gas sample at room temperature, and from that you extract, of course, a Doppler broadened profile. But as you can understand, it's quite a challenge of extracting kilohertz level of accuracy from such a broad profile. So that's why we also employ a cavity, at least also for the length enhancement. So our high finesse cavity of 150,000 finesse has roughly an equivalent length of 50 kilometers. And of course, we get power enhancement of the counter-propagating beams of somewhere around 150 watts. And that allows us to do saturation spectroscopy. So for the molecules flying orthogonally to the beam, we have interaction with both beams at the same time, which allows us to deplete the ground state with one beam, and then we see less absorption, which then comes in as a narrow Doppler-free lambda dip. However, even after the length enhancement and the powerful beams, we only have around 10 ppm of absorption after this 50-kilometer interaction, which is getting near the level of the photon shock noise. So we need some very accurate or very sensitive method to extract these small signals, and that's why we apply the technique called NISOMS, which stands for noise immune, cavity enhanced optical heterodyne molecular spectroscopy. Essentially, this is just frequency modulation spectroscopy within a cavity. So we modulate our laser with two out-of-phase sidebands, where we need to ensure that the modulation frequency is exactly the free spectral range of the cavity, and that then allows us to perform frequency modulation spectroscopy within the cavity. So be aware that we do a phase-sensitive detection. So we do a dispersion measurement, and I would like to go slightly into this. So normally, so you can then picture the light-matter interaction, so the molecule interacting with both beams, as you have then the susceptibility, where you have the real and the imaginary part. The imaginary part is the absorption, but we are with NISOMS sensitive for the dispersion. So we acquire these kind of dispersive line shapes. So that is then the direct NISOM signal, which is this dispersive line shape. But in order to reduce noise even further, we also apply within the spectral profile a wavelength modulation, which is a second layer of modulation, which then gives us a derivative detection. So then the signals we extract can either be the 1F or 2F, so the first or second derivative, which looks like these kind of line shapes. So this is then the first derivative of a dispersive Lorentzian or the second derivative. So this is the dumbed down version of our setup schematically. So we have our diode laser, which is doubly modulated for locking purposes and for the spectroscopy purposes. Then afterwards, we capture the light in a photodiode going to our high-speed lock-in amplifier, which also gives us the second modulation of the piezo. And of course, a very important segment is, of course, the referencing with the optical frequency comb, which is referenced to our in-house atomic clock. So to show us that the setup is indeed working correctly, these are some typical ordinary measurements in water. So water is a nice benchmark molecule, giving some strong resonances. Here we recorded at a low pressure, and the single scan, only taking a few minutes, we can already easily get a signal noise of 1,000 and get accuracies easily of around 5 kilohertz for a single scan. This is then the 1F measurement, of course. So this is then results in HD. As you can see, the line shape is all over the place. So this is earlier published for the R1 and the P1. So you see it's complex, and you see also stuff is going up and going down. And for the P1, you can even say it's almost completely inverted. And remember, if something goes up here, it means increased absorption. So we see, instead of saturation, we see an inverted type of saturation. We see absorption going up. So what's going up then? In the previous talk, you were kind of an explanation which matched with the R1, but we also analyzed a different effect, and that is the so-called crossovers within the cavity. So I explained to you the saturation scheme, but next to that, you can also have the situation where you have a molecule flying with respect to the beam. And if you have a split excited state, where if your molecule can overcome the Doppler shift in between, you can also have a saturation scheme like this, coupling to two excited states. And this will then also form as lamp dips in your spectrum. You can get even a little bit further. You can also have the other case where you have a split ground state. And if you have a particularly large relaxation parameter, you can then pump the population from one state to the other ground state and see an enhanced absorption. That we can see these kind of crossovers, we also did an analysis in H2O17 where the hyperfine is rather large. And indeed, here you can see that with our setup, we could resolve the hyperfine splitting of this specific transition. And right here in between, you see a crossover appearing. And this is the V-type crossover. So you see an additional lamp dip. You can also see that it's difficult to predict where crossovers will appear because naturally you would expect one here as well, but you see it's absent. So then if we move to the HDP1 level structure, for example, you see that the excited state is split with only 45 Hertz. So you can assume this is like a near degenerate state, and you have 5 different ground states equaling to this hyperfine stick spectra with the imposed positions of the possible crossovers. If we then do a density matrix simulation, where we use a set of coupled Bloch equations where we integrate over the velocity, detuning, everything, and we do a parametric sweep over the relaxation parameter, we see that for a certain common set of parameters, we can actually get numerical output, which rather well agrees with the two shapes of the P1 and the R1 transition. However, the origin of this relaxation parameter was not yet fully resolved. We also see that indeed we see then the hyperfine transition center is a bit shifted from the observed peaks from these simulations. So then naturally the question is, what about the R0? Because in principle it's an inverted case of the P1 transition. So here we would expect then only the V-type crossover, so lamp dips in our spectrum. As you can see here. However, the R0 is not observable in a room temperature cavity, as it is the transition is exactly on top of one of the strongest water transitions in the band. So we need a cryogenic setup to freeze out all the water. That's what we did. So these are some preliminary results for the first for our first measurement in R0 at 59 Kelvin. And you see again, we get this kind of dispersive shape, something narrow going up and then a broad tail going down. So not what we expected from our crossover model and approach. However, if we have we can then assume like a preliminary result. We believe that the transition center should be somewhere within here. And again, comparing with theory, we see it's 2 megahertz off. So this is then the overview of what we did. We observed and measured many transitions, or also earlier published. So there are R0, R1, R2, R3, P1, and P3. And the interesting thing is that the R1, R3, R3, and the P3 all have the same spectral profiles. The R0, since it was cryogenic, was a bit narrower, but it's also looking the same. But at least these fours are all looking the same, except for the P1. The other interesting fact is that we see that with respect to theory, we have a very constant offset. So theory is always 1.9 megahertz below the assigned peak position to us, which is also a rather interesting observation. So now I will give the hand to Meissa, who will continue about the rotational intervals.
Okay. All right. I'd like to continue then the talk. My name is Meissa, and I just wanted to add from the previous slide that P3 was just newly measured, so it was never saturated before. So thanks to the fact that we have another possibility to use a laser in a different range, we can access P3 and then do this kind of overlap and maybe extract some rotational intervals. So in this case, we're going to use three types of transitions, so the R1, P3, and R3, so that we could extract then the rotational splitting in the ground state between J1, J3, so the quantum number, and then the rotational quantum number 2 to 4 in the excited state. I just wanted to introduce now that we use a second order of the modulation to be able to increase the signal to noise. So from the R1, we expected this kind of dispersive line shape. As you can see on the right side, you can see the water, the normal water saturation profile, which is a normal lamp dip for the 1F. And then if you use the second demodulation, we increase our signal to noise up to 10, which makes it easier to measure P3 because it's much more weaker than P3. And as you just realized from main question, P1 is already 5 orders of magnitude weaker than R1. Then can you imagine P3 is 10 times weaker than R1? So we need to use the 2F. Anyway, as you can see here, the line shape also don't match as well because the line profile is not very well defined. So we continue then, and we wanted just to show this kind of overlap that can be done and how well the shapes look alike between the R1 P3 and between the R3 and P3, one on the left and one on the right side. And to be able then to do this kind of rotation, we use this correlation function to see how well the shape match and to be able to extract basically the maximum overlap possibility. As you can see, it matched pretty well from both sides, and there's like a 95% overlap around the center. So this is quite nice. But unfortunately, from this cross correlation or an autocorrelation, it's very hard to be able to extract any uncertainty from this kind of analysis. So then we have this idea of using some kind of trick of cubic spline function, where we start with like a normal R1 function. We extract out with a cubic spline extrapolation. And for example, on the bottom side, on the left side, you see the P3. And then what we can do from this cubic spline interpolation, we get our set of parameters that are fixed now. They don't move at all. And we only have 2 degrees of freedom to do this last fitting, which is basically just the amplitude and the delta, so the lag we call, or the position in respect to the R1. And from this, you can clearly see that the fit is pretty good, and you have this residual right here, and we can also extract a certain uncertainty. So the next slide is the overview of basically the above overlap, and the top side is the correlation part, which I explained earlier, and the bottom side is using this cubic spline to be able to extract some kind of uncertainty. To be noted that both of these analyses both give the same extraction of this rotational interval within 2 to 3 kilohertz, but then we fix the uncertainty to 5 kilohertz thanks to this cubic spline way of doing the extrapolation. So it helps us, and then we continue because there's this additional obvious effect is due to the Hyperfine spectra, because in R1, R3 case, it spans its very broad range, and also the center of mass of the Hyperfine spectra can give rise to additional issues. So if you use a simple type of simulation, very, very simple, like really crude, we don't do any optical log equation, we just put the 1F dispersive variation that my colleague explained earlier, and we just use a convolution with all the hyperfine structure, you can clearly see the maximum of this 1F is shifted compared to the center of mass. So this can give rise then to a certain discrepancy, or we could say when we overlap both of the beam, then one of the center of mass will be higher than the other one. And then this gives rise to our main final uncertainty. If you look at the uncertainty budget, where we have almost no pressure or power effect here, because there's a common mode that gets rid of this part. The statistic is then described by this cubic spline I explained earlier. And lastly, we mostly determined by our hyperfine extrapolation, very crude one. So, and then if we want to compare with theory, we have then these numbers, and as explained in the Rovibrational, it was plus 1.9 sigma off, and in our now new analysis of the rotational interval, we have plus 1.5 sigma of theory. I just wanted now to show some scientific installation that we could have when we use some theoretical value, and also some homework that I want to give to our colleague, and hopefully they can help us. All right, so just the V0 J equals 1, J equals 3 of HD, you have mostly dominated by the E5, which is 10 minus 4, around 2 megahertz. So anyway, we're not looking at the levels, we're looking at transition. So thankfully, there's still this cancellation error that was explained by Frederick earlier. And in our case, we're still limited by E5, which is 3 10 minus 6, and it's still dominating also the total uncertainty of these rotational intervals. And I come to some kind of conclusion at the beginning. I just wanted to say that we successfully saturated R0 for the first time, well, with our Chinese competitor as well. And we measure a total of 6 HD lines where all of them looked alike, except it for the P1, and theoretically constantly shifted by minus 2 megahertz. And the line shape spectra of the vibrational transition HD is still a puzzle. And if you could solve it, if we could even resolve one hyperfine transition, that could help us to go normally below kilohertz if we put much effort to do it. Anyway, we then use this combination differences to be able to see extra effect or some additional rotational transition. We could compare the theory, and we can clearly see that we are limited by the E5. And anyway, this measurement will also be an improvement in the rotational interval by 1 order, except for the R0 that was measured directly without any of this vibrational transition. This was accurate to 25 kilohertz, and theory is accurate to 33 kilohertz and is 0.7 sigma off. So it agrees quite well, but still in, I don't know if it's a coincidence, but still agree in the left side, let's say. So there's still this plus and minus issue. And then come my homework then. This is also a paper that was shown by Frederick. And basically you can clearly see that the dissociation energy here, I don't care about it because I do vibrational, so I jump directly to the rotational part where it's still limited by the E5, but it's actually way more accurate for this. And this is in H2. And my question would be, could you do the same thing for HD? Because you could do, in this paper you did for all the other isotopologues, you managed to have higher accuracy than we have. And I would expect if it was possible to reduce the E5 for the rotational intervals, maybe we could see something new, or see if we could do more tests on the E5. So that's the homework. And I would like to finish with the outlook right now, because we could do even more additional combination if you go to the cryogenic setup with R0, P2, R2, and P2. And if you have then high accuracy, we could be able to do more tests on QED and so on. And we expect to have high accuracy because we have narrow line width there. Okay, line shape model is still an issue even for the rotational interval extrapolation. And just to tell you that this line shape in HD only occurs when we have cavity and standing wave and saturation. It never occurs in the experiment of Samik, or basically I just write the first author of this paper, where he did it in both HD and D2 for the 0 to 1 transition in a molecular beam experiment, and the lamp shape was perfectly fine and symmetric, and it could have really nice accuracy. We first thought in the beginning, as explained by my colleague, that it was the Hyperfine issue, and then crossovers might create this issue of the line shape. But it doesn't look to be the case because, as you can see, R0 was different. And then we had other idea, which was similar idea with a Chinese colleague, that maybe the standing wave can have an additional effect. And in our case, we're thinking because we're only saturating at low velocity, we're only looking at velocity that are really low. And then this standing effect can create some kind of trapping that could destroy one of these three coil doublet. One is saturated absorption on the left side, on the right side, and then you will have a stimulated emission on the left side. And one could be destroyed by this standing wave optical lattice and give rise to this kind of asymmetry. In the near future, the spectroscopy, we will do more spectroscopy on other isotopologue of HD, of molecular hydrogen, just like HD, which is radioactive, and it is a challenge to have a nice cavity and measurement on it. But hopefully it will work, and we will have maybe more ideas of what's happening to the lens shape on molecular hydrogen when we do saturation. And with that, I would like to thank you and my team and all this, the funding. So thank you very much.
Thanks very much. So we got back in time. I see there's some questions there, but Christoph has a strong urge. Okay. Shuming. Yeah. Hi, Shuming. Good to hear. Interesting results. I have two questions. Could you tell what are the adjustable parameters in the modeling of the line shape? I guess that's the relaxation parameter, yeah, that you talk about. And second, do you have a guess why the P1 line is so different from other lines?
Well, we thought we had a guess. That was that's why indeed. So Shuming, your colleague indeed showed that earlier we had we used a different way to estimate the line position for the P1 as we're using this model that we were just saying, and this model just barely changed with the relaxation parameter, so gamma currencies and the gamma population, which was varied, and you can actually see them in the paper, on the P1 paper, what was the relaxation parameter used. But as you can see, the R0 would not work if we actually did it. The optical block equation then would not work. We need additional things. And what was the second question? Sorry. Yeah, the shape of the P1. Unfortunately, we've shown it. We've done it many times. We redid it actually in a cryogenic situation, and it was still the same. It was mostly going up, and also showing. Here you can see also that our shapes also not totally the same even for the R1, because our line go higher and it goes lower. So also maybe something to see, maybe the difference between TRDS and ISON, because you have a decrease in power over time and you do modulation to extract a line. So maybe that's something to look at, because as you can see here, a line goes higher than it goes lower, because you go to like some kind of a value of 30 nanovolt and go down only to 20 nanovolt. One is narrower, one is broader. So we'll see. We have to discuss and see what we can do with this.
So would it be an option to pump this hyperfine transition with microwaves while you record the spectra to try to figure out what the role of the hyperfine structure is?
From the concept, probably yes, but what do you want to answer? Fine.
Well, the new cavity is difficult to get microwave in, that's for sure. We can potentially try it in the old setup, which is a glass cavity, so that's easy to get some RF field inside. But to get it homogeneous along the whole cavity length is, I think, a challenge. Yeah.
So our cavity is 40 centimeter, 20 centimeter, and it's mostly technically issue, but it would be interesting if, yeah, maybe it would be possible.
I wonder, so first of all, thanks for the interesting talk, course. But I wonder what the meaning of these error bars, for example, and there are many plots like this, and I always get very worried when the chi-square is 0.
Well, this error bar coming from a multiple scan, and just like Leslie was explaining, like the standard error of mean. So we have for the P1, I don't remember very well now, it's been a while, been 2 years, 50 scans or 40 scans, and then we average them, and we have this error bar. And in the R1 case, it's so much stronger that we don't have any error bar. But maybe, yeah, can you see your point? Yeah. Deviation.
Same point. Yes, he has an urgent.
No, I don't have. No urgent. He's been patiently waiting until the questions. So thank you very much for the talk, because it shows a limitation of the theory. So let me say what I think is for our side is, to my opinion, it comes from the so-called beta logarithmic correction, this discrepancy, which we are not able to calculate with the four-body systems. In fact, we have done such a correction only for the ground state. And for the ground state, at dissociation energy, we have a perfect agreement. For all other states, we have to rely on Born-Oppenheimer approximation. What does it mean? It means that one has to perform the calculation of beta log n for each vibrational and rotational state with four-body calculations. So let me give you the scale. It will be of 10, maybe 100 million of computer hours to do the calculation. It is possible. It simply takes our time and also computer time.
Do you think it's worth it to take your time?
Yes, but it means probably our time is also not. So we have limited resources, but anyway, this is a very important trigger for us. So certainly you may expect 1 year we shall have a result. We already maybe started, but we are considering this fully four-body and beta calculation beta logarithm for all these vibrational potential states. Thank you.
Okay, thank you.